to Unit 9 review for our final exam. Is the graph a function? If it passes the vertical line test, then it's a function. So this does pass the vertical line test, so it is a function. Is the inverse a function? Well, that does not pass the horizontal line test, so we're going to have to say no to that. Is the graph a one-to-one function? No, because a graph that passes the horizontal and the vertical would be one-to-one. This fails the horizontal line test. Sketch the inverse of the function. All right, well, on a program like this is going to be a little tough for me. I'll try my best using the ordered pairs. Basically, it's a reflection in the line y equals x. So you flip the ordered pairs. xy becomes yx. So negative 1, negative 2, negative 3, negative 1 becomes negative 1, negative 2, negative 3 here. Negative 2, 1 becomes 1, negative 2. 0, 1, 2, 3, 4 becomes 1, 2, 3, 4, 0. 2, 2 becomes 2, 2. 1, 2, 3, 4, 2 becomes 1, 2, 1, 2, 3, 4. So we're flipping those ordered pairs, and then we just connect them the best we can. So this went here, that one went there, so that one gets connected, then we connect back to here and up to there. And what that is showing is that that's a reflection, and this isn't going to be perfect, I'm trying, but in the line y equals x. Okay, likewise, there is a line y equals x through here, and we can reflect this as well. So this point, negative 2, negative 1 becomes negative 1, negative 2. Reflection in that line. 0, 1 becomes 1, 0. And if we stay consistent with our reflection, it would look like that. Okay, now verify that these are inverses of each other. All right, well, I'm not going to do both of these problems. Actually, 5 is probably a tad bit easier than this one. I'll do this one. But basically, when you do this, you have to show that f of g of x equals g of f of x, and that both of those come out to the variable x. So we'll try doing that. Take g here and put it in for this one. So we got 3 times, instead of x, we're going to say x plus 4 over 3. That's 3x and then minus 4. Well, don't distribute through. We're just going to cancel the 3. So this becomes x plus 4 minus 4, which is equivalent to x. Over here then, we have to do the other way around. Take this here and put in there. So that becomes 3x minus 4 plus 4 all over 3. Well, those cancel. We get 3x over 3, which is equivalent to x. So since we were able to show that, they are inverses of each other. Very similar for number 5 there. Okay, I am going to do each of these. Algebraically find the inverse. So this is the one where we switch the x and y and then solve for y. So this problem, first of all, the domain and range. I can state the domain of the function right now. X cannot be 0 or negative infinity to 0, union 0 to infinity in interval notation. But we cannot have 0 because right off the bat, that would make undefined. So what we do now to find the actual range of this is we find the inverse and then we find the domain of that inverse. That's how we go about that process. So x is equal to y plus 4 over y. Change both of these out. All right, well, I'm going to multiply both sides by y because I want to solve for y. And now I have xy equals y plus 4. I got to get the y's to one side, all right? So what I'm going to do is subtract 4 from both sides. And at the same time, I'm going to subtract xy from both sides. The 4's cancel here. We'll have just a negative 4 left on that side. And now over on this side, I'll have y minus xy, which I can't put together. Now I'm going to change color for this step because this is the step most have a hard time remembering, but you can literally factor out a y and have 1 minus x. It's not negative x, it's 1 minus x. Remember, when we distribute through, we want to have that same thing. Okay, so we've got this. Then all I have to do is divide by 1 minus x to both sides. And I have found the inverse. This is the inverse right there. Now remember, that's the exact same thing as positive 4 all over x minus 1. These two are identical to each other because you change the sign. And some people might have that if they did this problem a tad bit differently, but it's okay, it's the same. Either way, the range is the same, the range of this function is the same as the domain of this inverse. So we have x cannot be 1. Okay? Interval notation is obviously a little bit different. Okay, so trying this one here, this is huge. This tells you the domain of the function. It's literally called a domain restricted function. So you have 4 to infinity if you want to go interval, or just write this if you want to go that route. But bottom line is, this is a one-to-one function if we limit the domain. So let's go find its inverse. So x equals y minus 4 quantity squared. And to get rid of the square, we take the square root. So we have root x equals, and here we have y minus 4. So when we add the 4 to both sides, I'm getting the inverse coming out to root x plus 4. So that is the inverse for this one right there, root x plus 4. And the range of this function is the same as the domain of this one. And we cannot have negatives. We can have 0, that's fine, but we cannot have negatives when we have the square root like this. Okay, convert to exponential form. This we've been working on a lot, so I'll just do that real quick. 4 to the negative third equals 1 over 64. And likewise, 3 to the negative fourth equals 1 over 81. You should be pretty comfy with doing that by now. Blast to the past here. Sorry, I'm not ready to graph yet. Let's do these. Now we're going to logarithmic form. The base becomes the base, so this would be log base 3. And what do we have? Well, we've got 3 raised to the y power, so that would have to be on the right side. So we've got 3 to the y equals x. That's all checking out. And likewise, the base becomes the base. So log base 4, 1 over 16 equals negative 2. So you're good with those, hopefully. Find the exact value of the logarithm. Don't forget, we're basically just look down here at the base. How many times do we multiply that base by itself to get 27? Well, that's 3 times 3 times 3, so the answer to this problem is just 3. 2 to what power gives you 32? Well, that would be 5. 2 times 2 times 2 times 2 times 2 is 32. All right, so now graphing these functions. Remember with these we did key points. So basically you notice right here that we are going to graph, I'm going to try to find space here. We're going to graph 2 to the x power. Now I'm not going to consider the transformations when I come up with my key points. That just says left 1 and down 3. So left 1 and down 1, 2, 3. So I like to put an x there because that's my starting point. Now we know exponential functions will have a horizontal asymptote. So I can already write in my asymptote is y equals negative 3. Okay, so but my key points, I'll do those in red here, would be if we were to plug in negative 1, if we were to plug in 0, and if we were to plug in 1. What would that look like? Well, if I put in a 0, we know we're going to get a 1 all the time. So that's this point right here relative to our new origin. 1 comma 2, 2 to the first is 2, so over 1 up 2. And then negative 1, 1 half. 2 to the negative first is 1 half. So left 1 up 1 half. Okay? And knowing what exponential functions do, we can sketch that there. So the domain would be all real numbers in interval notation, and the range is dependent on this horizontal asymptote, so negative 3 to infinity. Okay, next one here is the same kind of idea, it's just shifted up 1. So I'm going to go up 1, and we have a different base. Okay, so the 3 key points would be negative 1, 1/3, 0, 1 still, and then 1, 3. So when I go plot those points from the new origin, which is really right there, because we shifted it up 1, I'm going to have negative 1 up 1/3, 0, 1, and then over 1, 1, 2, 3. And we have our exponential. Y equals 1 is that horizontal asymptote. The range is negative infinity to infinity. And then, did I say range? The domain is negative infinity to infinity. The range is 1 to infinity. All right, so these are exponential functions. All right, I didn't have a base e on this practice. I could have easily done an exponential. That's one thing you got to understand. If that said e to the x power, that's not a logarithmic. Just because there's an e in there, it's still exponential. So exponential, we know, with base e has approximately 2.7. All right, well, these both have a base of e, but they're logarithmic problems. So we're still going to go like this one, left 1, down 3, like we're used to doing, but logarithmic forms look different. They have vertical asymptotes. Why do they look different? Well, they look different because they're the inverse of the exponential. So this one flipped, remember that line y equals x is gonna look different. Well, let's think of our key points now. Do those in blue. The key points down here, okay, for the exponential function, there's a few things going on here because we got a stretch to talk about. Should we take a break? Take a stretch? Oh no, we'll just stretch within the problem. All right, so basically, I know, bad jokes. All right, so here we go. We're gonna put in and consider e to the x power. If I put a 0 into here, I get a 1. Okay, if I put a 1 in here, I get an e. If I put a -1 in here, I get a 1/eth. Okay, knowing all along that e is 2.7. But here's the deal. We need to flip all of these ordered pairs. Okay, we need to flip these. Why do we need to flip these? Because we're not actually graphing e to the x, we're graphing the natural log of x. So I'm not going to rewrite all these because I'm talking to you here, but instead of 0, 1, we're going to graph 1, 0. But here's the other thing, we have to consider the stretch. So whatever we normally would do up and down, we're going to do twice that amount. Okay, so this is, maybe I will rewrite them, I don't want to confuse you. That's 1, 0. Well, it's going to be over 1 up 0, and stretching that doesn't make sense for this point because it's times 0. Now this one is not 1e, it's e1. So when I stretch that, I don't really go up 1, I actually go up 2. So from here, over 1, 2.7 up 2, like right there. Same with this one. It's not really this point, it's 1/eth, comma -1. But again, it's -2 because we're stretching. So over 1 over 2.7 down 2 would be like right there. So this has a little stretch factor to it. All right, well the domain now would actually be -1 to infinity, whereas the range turns into all real numbers. And the asymptote turns into a vertical line, which is x equals -1. All right, going strong here. Here we go. Last one on unit 9. We're going to go right 1 up 2. So right 1 up 2, and I'm going to make my x there. I know that there's a vertical asymptote because that's what logarithmic functions do. X equals 1 for that equation, okay? And then we're going to do our key points again. So again, they're all right here. I mean, they're all right there. Whoops, that one right there. So basically, we're going to go from this spot 1, 0, which is right here. E1, the reason there's no stretch or no flip on this one. So 1, 2.7 up 1 to right there. And over about 1 over 2.7 down 1. So basically, we have that. The domain would be 1 to infinity. And then the range is all real numbers. And then you should be feeling like this. That was cool.